Hello friends, in this video let us discuss about the phasor diagram and the characteristics of your AC series motor. So if you look at the schematic diagram of your AC series motor, so here we are having the armature and these are the stationary brushes, and this is your main field winding and this is your compensated winding, and here we are having the interpoles and a non-inductive shunt resistor, and from here you are providing a single phase AC supply. So the interpoles are designed to reduce the sparking occurring at the brushes. The compensating winding is provided to neutralize the flux of the armature circuit, and the main field winding is to develop the necessary torque. So in order to reduce the reactance, because the power factor is directly related to the reactance of the main field winding and the armature circuit reactance. So in order to improve the power factor, we are reducing the number of turns in the main field winding. So to reduce the reactance of the main field winding, we are considering here more reactive voltage drop. So in order to reduce the reactance and to improve the power factor, we are considering more reactive voltage drop in the main field series field winding compared to the armature circuit and the compensated winding reactance. So here you will be witnessing less reactive voltage drop compared to the main field winding reactive voltage drop in order to improve the power factor. So now here the flux phi is produced by the current I, that is the armature current. So the flux phi lags behind this armature current by a very small amount that can be neglected. So let us see, this is my current I and this will be my flux phi. So I am drawing them in one phase, neglecting the phase lagging, that is the flux phi is lagging behind the current I. So neglecting that amount of angle, lag angle, I am drawing them in phase. So current flux phi is in phase with the current I. Now here if you witness, here we are having, in case of a DC transmission, here we are having the resistive drop in the series field, resistive drop in the compensating winding, resistive drop in the armature circuit, and the resistive drop in the interpoles in case of DC transmission. But in case of AC transmission, in addition to the resistive drops in the respective windings, we are also witnessing the reactive drop in all the four windings. So now here the resistive drops will be in phase with the armature current, whereas the reactive drops will be in quadrature with the armature current, and they will be leading 90 degrees to the armature current. So here if I take, this is my point from where I take my reference phasor, that is the I, or you can say the flux phi. So from here I am having the first resistive drop I into R, that is a series field resistance drop, and this is my series field reactance drop. So again here having my next, the compensated winding IRC, this will be IXC, so this will be IRP, that is the interpole resistance, and this will be IXP, this is IRA, this will be IXA. So this is your terminal voltage V. Now here if you see the phasor length of IXE, that is we are taking a more reactive voltage drop in the series field compared to the other compensated winding, armature windings and the interpoles, in order to improve the power factor by reducing the inductance, that is the reactance of this main field winding. So thereby we are drawing this phasor to a greater length compared to the other phasors, reactive phasors. So here we will see the flux, when the flux phi is 0, we will be having your generated EMF will be 0. So when the flux phi is maximum, we will be witnessing your generated EMF to be maximum. So since the graph of the flux phi and the generated EMF cross the 0 cross the 0 point at the same instant, and also they cross the maximum values at the same instant, that can be that means the E can be in phase, exactly in phase with phi, or exactly opposite in phase with phi. It may be exactly in phase with phi or opposite to the phase phi. But in case of motor, the generated EMF or the generated voltage will be always in opposition to the current I. So the voltage will be in opposition to the current I. That means you are having your counter EMF in opposite phase opposition to the current I. So here this is your counter EMF, and here this will be your counter EMF which got reversed. This is your reverse counter EMF. Now the terminal voltage drop will be equal to the summation of the resistive drops across all the 4 windings, as well as the reactive drops across all the 4 windings, and also the summation of these counter EMF minus E. So this is all about your phasor diagram. Now coming to the characteristics of your AC series motor, first of all let us take the first characteristic is power output. So the power output of your AC series motor is the product of, that is a mechanical power developed by your AC series motor will be equal to the product of counter EMF E and the armature current. So here, as you increase the current I, there will be decrease in the counter EMF, but compared to the magnitude of this EMF, the decrease in the value of E is very less. So you can neglect the decrease in the value of E as compared to the magnitude of E. Thereby you can consider that E is proportional to I. So therefore you will be having a proportionate increase in the current. That is, a proportionate increase in the current will increase the EMF. There will be having the proportionate power output. So your power output will be proportionate to the current. So here this value, the decrease in the E will be negligible compared to the magnitude of E with the increase in current. Therefore you can consider the power output is proportional to current. So let us draw the characteristics here. So this is my current. So the power output is almost proportionate to the current. So let me draw, this is my power output. So the next thing is you are having the power factor characteristics. So the cosine of the phase angle of the AC series motor is known as the power factor of your motor. So that is cos phi, the cosine of the phase angle is known as the power factor of your motor. Now from here, this will be your phase angle phi. So from this phasor diagram, you can write your sin phi will be equal to I into x sc plus x c plus xp plus xa. That is the reactances of all the 4 windings. So if you draw like this, and if you see the sine angle, the sin phi will be equal to I upon, this will be V. Let us consider this is I into x, that is the effective reactance x upon V. Now from here, your cos phi will be equal to under root of 1 minus Ix upon V square. So the power factor, you can improve the power factor by reducing the drops, reactive drops, that is making the reactance drop less and increasing the counter EMF. So you will witness the reduced reactance drop and the higher counter EMF at low loads. So at low loads you will be having higher power factor, and as you increase the current, then there will be the drop in the power factor. As you increase current, there will be the drop in the power factor. That means at overloads, so at overloads and at starting, you will be having the low power factor. So this is exactly in reverse to the induction motor and the transformer, where we are having good power factor at overloads, but here at overloads and starting we are having very poor power factor. So the power factor will be decreasing with increase in the current. Now the next characteristics you are having is the speed and current. Speed and current. So now here we have seen, in case of DC transmission there are only resistive drops, but in case of AC transmission, in addition to the resistive drops, you are also witnessing the reactive drops in the 4 windings. Therefore the counter EMF generated will be less, because as we know the E is proportional to phi n and E is also equal to V minus voltage drops. So now as you witness here, as the counter EMF generated on applying the single phase AC supply, you are having less EMF compared to the DC system or the DC transmission or the DC series motor, you can say. That means you are having a drooping characteristics. So if you see the DC motor speed current, let us say this is N, this is I, so you will be having these speed current characteristics for your DC series motor. So you will be having more drooping characteristics as the generated EMF is less compared to the generated EMF in your DC series motor. So the characteristics will be like this. This is for AC and this is for DC. So here this will be my speed current characteristics. This is, let us say N, this is our power factor for these characteristics is. Now again we will be having the torque current characteristics. The fourth one is torque current characteristics. So the torque here will be directly proportional to the product of phi and the armature current I. Now if you neglect the phase angle between the phi and I, then you can write the torque is proportional to I square, neglecting the saturation. Now if the magnetic circuit is saturated, that means the flux remains constant and your torque will be proportional to I only. So your torque will be proportional to I. This is your torque on saturation of the magnetic circuit. Now we have known the torque current characteristics and the speed current characteristics. From here you can determine the torque versus speed characteristics. So your torque versus speed characteristics, this is speed and this is torque. So this will be for DC and this will be for AC. So you will be having more drooping characteristics compared to the DC series motor. So this is the torque speed characteristics. Now the operating characteristics of your AC series motor is very much similar to the DC series motor. However, in case of your AC series motor, you will be having a very poor power factor because of the high inductance of the series field winding and the armature winding. So you will be having low power factor and the efficiency is also less because of the eddy current losses, and the poor power factor. So due to the poor power factor, you will be also having the low starting torque of the motor. So due to the poor power factor, you will be having low starting torque, and for a given kilowatt rating, the series motor is 1.5 to 2 times greater in size and weight compared to your DC series motor, and the cost of your AC series motor is also very much more compared to your DC series motor. So the advantage of the AC series motor is here you can control the speed. The speed of your AC series motor can be controlled best by the solid state devices and also controlled by providing taps on the transformer, which is not possible in your DC series motor. So in this video we have learned the phasor diagram and the various characteristics of your AC series motor. So I hope you understood well. Please subscribe to the channel. Thank you.